Okay, this is the Math 1813 final exam review for pre-calculus, prep for calculus. So for question 1 here, part A, I'm going to find the domain for the function h of x is equal to x plus 2 over x squared minus 3x minus 10. Right? So what we're going to want to do here is first break up our denominator into something that we can see if anything cancels out with our numerator. So we want to know what's going to multiply to give us negative 10 and add up to give us negative 3. So that's going to be x minus 5 and then x plus 2. I have an x plus 2 and an x plus 2, right? So you can cancel those out, and essentially we're going to have a whole at x is equal to negative 2. The thing we want to do is set our denominator equal to 0. So we're going to say our new function h of x is equal to 1 over x minus 5. So we're going to say x minus 5 is equal to 0. So x cannot be equal to 5 because that means we have a 0 in our denominator. That means that we have a function that doesn't really work, right? So now what we can say is if we draw like a little number line, we have this value of negative 2 and 5. We know we're going to have undefined functions. So we're valid anywhere on either side of them and in between them as well. So we write that interval notation. It's going to be from negative infinity to negative 2. The union negative 2 to 5. Then union 5 to infinity. Now to look at part B. We're given g of x is equal to 1 over the square root of 1 minus x. So we can't let our denominator be equal to 0, right? So we're going to set the square root of 1 minus x equal to 0. Square root, so that square root, nothing can be negative or 0, or 0, right? So we need to find what values make it positive. So if we plug in, or if we square both sides, square, 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 we have 1 minus x is equal to 0. So when x is equal to 1, our function is equal to 0. So we know that we can't have anything there, right? The next thing is, since our denominator is a square root, we can't have any negative values. So that means that x needs to be less than 1. Because anything greater than 1 is going to give us a negative inside of our square root. Or if anything less than 1, we're going to have like negative, let's try negative 2. We'll have the square root of 1 minus a negative 2. Which is going to give us the square root of 3, which is a positive value, which is fine, right? So what we're going to do is we're going to draw a little number line here at 1. 1 doesn't exist, and we know we can only exist this way, right? So we're going to say that from negative infinity to 1 is our domain. So for part C here, we're given k of x is equal to the square root of x plus 1 over 2x minus 2. So we have two factors on this one. We need to know when our denominator is equal to 0, because then we know we can't exist there. We also need to know when our numerator becomes negative values, because we can't exist there, right? Start with our denominator. We're going to set 2x minus 2 equal to 0. Add 2 on both sides. So we have 2x is equal to 2 divided by 2 on both sides. So that x cannot be equal to 1, right? I'm going to draw a little number line up in the top. So we have 1 here. We're going to have a hole because we know we can't exist there at all. Next, we want to know when our numerator is equal to 0 or greater, or right, when it actually exists. So we're going to say square root of x plus 1 is equal to 0. Square both sides, so x plus 1 is equal to 0. So we know that x is going to be equal to negative 1. That's going to give us a 0 value. But if we put anything less than the negative 1, right, we're going to have values that aren't existing. So we plug in like negative 2, we'd have negative 2. Write that a little better. Negative 2 plus 1, which is equal to the square root of negative 1, which doesn't exist, right? For anything greater than 1, negative 1, like 0, we're going to have the square root of 0 plus 1, which is equal to the square root of 1, which is okay to have. And then also, it's okay to have a 0 in our numerator. So what we're going to say is we're going to do a filled in point there. And we know that we're going to exist anywhere between -1 and 1. And we're also going to exist anywhere between 1 and infinity. So how we're going to write that in terms of our interval notation is we're going to write from -1 being included because it can exist there. Then we're going to go over to 1. Then we're going to union from 1 to infinity. So next we're going to go to D, and we're going to use the same concepts. H of x is equal to the square root of x minus b over x minus a, where 0 is less than a, which is less than b, so we know b is greater than a. So one thing we're going to do is, same concept as the last question, is we want to set x minus a equal to 0, because we know we're not going to be able to exist there at all. And so x is going to be equal to a. It's not going to exist. So if we draw a number line, we know we're going to have 0, a, and then b, right? So at a, we know that we're open circle, can't exist there. And then now we need to find out when our numerator is going to be a negative value, or is equal to 0. So x minus b, it can be equal to 0, but we need to find where it is equal to 0 to determine what it can be less than. 0, we're going to square both sides. So x minus b is equal to 0, so then x is going to be equal to b. We can exist there. We're going to have a circle, and so the only point is 0. So if anything that was less than b, right, then that's not going to exist. So we know that we can only exist when our values are greater than b. So looking at a number line, that means that our domain only exists when we're at b or greater. So we're going to write that as is bracket of b, because we can exist there, and then we're going to go to infinity. All right, now we want to look at question 2a here. So we want f of x is equal to 3x minus 1, and that's squared, right? Well, this one's f of -2. Let's just simplify fully. So what we're going to do is plug in -2 anywhere we see an x. So we're going to do 3 times -2 minus 1 squared. It's going to simplify down to 3 times -3 squared, where f of -2 is equal to 3 times -3 squared is 9. So f of -2 is just going to be equal to 27. Okay, now looking at part B, we still have f of x is equal to 3x minus 1 squared. So we now have f of -2 plus h. So anywhere we see an x, we're going to plug in a -2 plus h. So we're going to have 3 times -2 plus h minus 1 squared. So if we simplify this down, we're going to have f of -2 plus h is equal to 3 times -3 plus h squared. So now we have 3 times, that square makes it 3 plus h times -3 plus h, that 3 being multiplied to all of it. So now what we have to do is FOIL this out. We're going to so that stands for first, outer, inner, and last, right? So our first term is -3 times -3. We're left with 9. That's going to leave us with 9. Our inner term is going to be -3 times h. So we're going to have minus 3h. Our outer terms are going to be -3 times h. So we're going to have a -3h again. And then our last terms are these h's being multiplied. So we're going to have plus h squared. So if we simplify that inside, we're going to have 3 times 9 minus 6h plus h squared. Better way to write it is going to be 3. I'm going to distribute out that 3 and rewrite it in the correct order. So 3h squared minus 12h, not minus 12h, minus 18h h, and then plus 27, right? So that's what, so you can technically write this in any order. That's just the more formal order, or the more familiar order to write it in. So now we want to know what f of negative 2 plus h minus f of negative 2 all over h is, where h cannot be equal to 0. And we know what f of negative 2 plus h is. We said that was 3h squared minus 18h plus 27. We said f of negative 2 was minus a 27, and then all that over h, right? So we have 27 minus 27. Those are going to go to 0. So we're going to have 3h squared minus 18h all over h. So we have our two terms on top both have an h in them. So we're going to write this as h times 3h minus 18. And we can do that by factoring out a singular h. I mean, h over an h. Those are going to go to 1, so they're gone. And then we're just left with f of negative 2 plus h minus f of negative 2 all over h is equal to 3h minus 18. Okay, now looking at question 3 here, the graph of function g with domain negative infinity to 12 and inflection points 6.5 and at 5.25 is shown. So find each of the following. If it does not exist, write NA. So we want to know when it's increasing. So we want to see when our slope is positive. So one thing we can do here is I'm actually going to make this graph a little bit bigger. And I'm going to get a straight line for us. Okay, from here, I'm going to see is to know when it's increasing, we're going to have a positive slope. So we want this aimed upward. So we're going to have that positive slope until this 4 value. And then, but over here we have this negative slope, so it doesn't really work, right? Now here again, we're going back positive again. So we can say we are increasing from negative infinity to 4. We're not going to include 4 because at that exact moment we're not increasing. Then we're going to pick back up again from 9 to 12. So next we want to see where it's decreasing. And that's going to happen when our slope is negative, and also it's going to happen at the opposite of what we just said, or the only place left in our domain that we didn't say was increasing. It's going to happen at 4 down to 9. So from 4 to 9, up here as well to 9. So now I'm going to find our local maximum and our local minimum. So one thing I'm going to do is kind of just close off our bounds here, kind of just for visual purposes, right? So our local maximum is going to occur inside of this function at the highest point, right? We can't include over here, so that's going to make this 36.5 our maximum. 36.5 at x is equal to 4, right? Now the same thing for our minimum. So our minimum, we can see, is going to be right here. Our local minimum is going to be right here at negative 26 when x is equal to 9. Now, to determine what our maximum is, we're going to get rid of what I just drew, those boundaries. Absolute maximum is the maximum of the entire graph going from endless bounds, right? But we know we end right here. We end right here, right? So that's going to make our absolute maximum 68.5 at x is equal to 12. But our minimum, we're going off in this way to negative infinity forever and ever and ever, right? So we aren't going to have a local minimum. We're going to say it's not applicable. So next thing we want to do is find our concave up, concave down. So concave up. We kind of want to know when our graph will hold something, right? When it's shaped upwards, like that, right? So if we go here and see that this area is going to be concave up, so we're going to say from 6.5 to 12 is concave up, and that's going to make our concave down. We're going down this way, right? It's going to be concave down from negative infinity to 6.5. All right, so now we're going to look at question 4. We have to find the limit as x approaches infinity for each of the following. So part A, so when y is equal to 1,000 over x plus 1. So we know as we're going to infinity in our denominator, it's getting very large. And it's growing at at a much faster rate than our numerator. So we're getting really close to 0, right? The way we can prove that is one thing is we just do y is equal to 1,000 over 1,000,000. Right? If we plug that into our calculator, we're going to get 0.000999, right? That's just going to continuously get smaller and smaller, and we're going to get so close to 0 where we're essentially just 0. So y is approaching 0 as x is going to infinity. Now looking at part B, we're saying that y is equal to 5 minus 1 over x over 2 over x squared plus 3. One thing we can see is that we're going to break it up. So as we're getting closer and closer to infinity, this 1 over x is going to be essentially 0 here. And this 2 over x squared is also going to be essentially 0. So we can say that our y is equal to 5/3, or it's approaching 5/3, as x is getting closer to infinity, right? So next, we're going to have part C here. Part C is y is equal to x minus 4 over 3x squared plus 1. So what we're going to do is notice that our greatest power is x squared. So we're going to divide both our numerator and our denominator by x squared. So we're going to have y is equal to x minus 4 over x squared over 3x squared plus 1 over x squared. So it's going to simplify down to 1 over x minus 4 over x squared, all that over 3 plus 1 over x squared. So we can see that 1 over x is going to go to 0 as we're getting really large and closer to infinity. That 4 over x squared also going to get the x squared is going to be really large and be 4 over a really large number, which is going to get really close to 0. That 1 over x squared here in the denominator, same thing, going to get really close to 0. So we're going to be left with y is getting closer to 0 over 3. So y is approaching 0 as x is approaching infinity. So next, let's look at part D here. There we go. Part D is y is equal to ax minus b over ax minus bx minus a. So same concept as the last one. We're going to say ax over x minus b over x over bx over x minus a over x. And we're going to simplify this. Those come, so we're left with a minus b over x over b minus a over x, right? So that b over x is going to get really close to 0, so we're going to say it's 0. Same thing with that a over x, 0. So y is approaching a over b as x is approaching infinity. Okay, looking at question 5, we are given two functions and we want to find out what f of x is and g of x is. So it says let f of g of x equal 3 natural log of 2x minus 1, and then g of f of x equals natural log of 6x minus 2. So we want to find out what f of x is and what g of x is. So we can kind of see that one of our functions is going to be some kind of natural log, right? And we also kind of see that one of the functions, we could say that 3x minus 1, and then that g of x is going to be natural log of 2x, right? Now let's just do a quick test. So f of g of x is equal to 3, times natural log of 2 of x minus 1. Another thing we can try, now g of f of x is equal to natural log of 2 times 3x minus 1. And now if we simplify that, we get that natural log of 6x minus 2. So we can say those are our two functions. And it's kind of just by looking at it and kind of trying to see what an interior function could be. Like if we looked at our g of f of x first, we could say an interior function was 6x minus 2. But now we look over at this one, we know that we don't have a minus 2, we have a minus 1. That's how we kind of said this was 3x minus 1, and that natural log of 2x was also another function. Okay, now looking at question 6, salt water is flowing into a large tank, and the concentration C of T of salt in the tank is given by C is equal to F of T, which is equal to 1.2 T over 100.6 T pounds per gallon, where T is in time in minutes after the salt water started flowing in the tank. So let's start off with question A here. I'm going to find F of 20 and explain what it means in terms of salt concentration and time since the salt water started flowing. So we want to know what F of T is equal to 1.2 T over 100 plus 6T. F of 20 is equal to 1.2 times 20 over 100 plus 6 times 20. So what we're going to do here to find out what F of 20 is we're going to plug it into our calculator and see that 1.2 times 20 is, so 1.2 times 20 is 24, and then 100 plus 6 times 20 is 220, which this is approximately 0.10909, repeating. And that's, and using our units, we know that's pounds per gallon, right? So we can say what's happening is at 20 minutes, the concentration of the salt water is 0.1091 pounds per gallon. So next we're going to look at part C. We want to find the inverse. So we know C is equal to 1.2 T of 100.6 T. We're going to find the inverse of this, right? So first thing we want to do is multiply both sides by 100.6 T. So that's going to leave us with 100 plus 6t times c is equal to 1.2t. Distribute our c, so 100c plus 6tc is equal to 1.2t. Next, we want to get all of our terms with t's on one side, so we're going to subtract 6tc. So we're left with 100c is equal to 1.2t minus 6tc. So now what we want to do is factor out our t value. And that's going to leave us with 100. Oh, didn't mean to go red there. 100c is equal to t times 1.2 minus 6c. So we want to solve for t. So we know that t is equal to, divide both sides by 1.2 minus 6c. So our t value is equal to 100c minus 1.2 minus 6c, which another way we can write this is f inverse of c is equal to t, which is equal to 100c over 1.2 minus 6c. So now for part C, we want to evaluate f inverse of at 0.15. So what we're going to do is take our inverse of c equation, which is 100c over 1.2 minus 6c, and we're going to plug 0.15 anywhere we see a c. So we have inverse of 0.15 is equal to 100 times 0.15 over 1.2 minus 6 times 0.15. And if we just plug this in, we're left with f inverse of 0.15 is equal to 15 over 0.3, which leaves us with 50 minutes. Right? So, writing this in, we're going to explain this in terms of words. And so that when the salt concentration is 0.15 pounds per gallon, the time it has been flowing is 50 minutes. Okay, now looking at question 7, we want to suppose the function f is related to a function g by the following. So we're saying that f of x is equal to 3g of 4 times x minus 5 to the minus 2. So whenever we're determining our shifts, we always want to start with horizontal shifts first, horizontal transformations first, I should say, and we should start with horizontal stretches or compressions. So we can see here that we have the 4, which is going to give us a horizontal compression by a factor of 1/4, right? So we're going to put that as our first one, and that's a compression by a 1/4 horizontally. And then next we'll look at what else is inside that creates a horizontal transformation. Well, it's going to be at x minus 5, and that's going to move it to the right 5. Right 5. Next, we want to move on to our vertical transformations. And again, we want to look at compressions or stretches first. So we can see this 3 here is going to be our third transformation. And it's going to be a vertical stretch by 3. And then our last thing is we have this minus 2. That's going to be our fourth transformation, which is just down 2. So let's go over to our chart and mark it. So we're going right 5 units. We said that was our second one. So we're going to write 2 there. We're horizontal compression by a factor of a fourth. We said that was our first transformation. And then we have shift down 2 units was our fourth transformation. And then a vertical stretch by a factor of 3 was our third transformation. Yep. So that is going to be the order that we would transform this function in. Okay, now we'll look at question 8. Bathtub was partially filled with hot water when the cold water tap was open. 2 minutes later, the bathtub held a total of 48 gallons. 5 minutes after turning on the cold water, the bathtub held 61.5 gallons of water. So, look at part A here. What was the rate of change in the number in of gallons of water from 2 minutes to 5 minutes? Well, first let's write a coordinate real quick. So, we know that we have time and we have our gallons, right? So we have 2 minutes, we have 48 gallons. Then we also have, after 5 minutes, we have 61.5 gallons. So for this one, we want to find the number of in gallons of water from 2 minutes to 5 minutes, the rate of change. So let's say our m for our slope is going to be equal to 61.5 minus 48 over 5 minus 2, which is going to leave us with 13.5 over 3, which is equal to 4.5 gallons per minute. So for this one, our rate of change is 4.5 gallons per minute. Now we want to look at part B. How many gallons of water were in the tub at the time the cold water was turned on? So we want to use our equation, general form, y is equal to mx plus b. Now using what we know our y in our case is n. We'll leave it m for now. X is t for our situation. We know our m, right? So we're going to say n is equal to m of 4.5 t plus b. We're going to solve for our b value for this question. So, how many gallons of water were in the bathtub at the time the cold water was turned on? So the cold water was turned on at 0, right? When time was equal to 0. So if we just plug 0 in for t, we're going to get n is equal to b, which that's not going to help us, right? So what we're going to do is use one of our points of 248. So 248. We're going to plug 2 in for t and 48 in for n. So 48 is equal to 4.5 times 2 plus b. So that 48 is going to be equal to 9 plus b. Subtract 9 on both sides. So b is going to be equal to 39 gallons. Now looking at part C, we're going to write a linear function for the number n of gallons of water at time t after minutes turned on the cold water. So we're going to continue to use the equation that we called for earlier, this n is equal to mt plus b, or that n is equal to 4.5t plus b. Now knowing that our b is 39 gallons, we can say n is equal to 4.5t plus 39, and that's going to be our equation right there. Okay, looking at question 9a here, I'm going to write a formula for each situation. Question 9a says median home prices in the U.S. were about $186,000 at the end of 2008 and fell by about 2.5% per year for a few years. So let M be the median home price and T number of years since 2008. So we know that 2008 is T is equal to 0. So one thing we want to do is use our equation that we have. It's like M is equal to our initial value, then 1 minus our rate to the power of t. So we're going to plug in our values here. So that M is equal to, our initial value is that 186,000, and then 6,000, and then 1 minus our rate says 2.5% per year. 0.5%. Well, to add this into our equation, we're going to have it in decimal form. So we're going to move this over, make it 0.025. So it's going to be 0.025, so we're going to plug that in, 0.025 into the power of t. And now just simplifying that, we're going to have m is equal to 186,000, then 0.975 to the power of t. So that's going to be our median home price. Next, we'll look at part B. Dan had an annual salary of $30,000 when he was hired, and has had annual salary increases of 3.2% each year since. Let D be Dan's annual salary and T be the number of years. So again, we want to use the same stock equation of D is equal to our initial value, 1 plus our rate, to the power of T. And for this one, unlike the last one, we want to use a plus T because we are increasing by 3.2%, where on the last one we were falling by that 2.5. So for this one, we're going to say our rate is equal to 3.2%. We want to have that in terms of a decimal, so we're going to say our rate is equal to 0.032. So we're going to say D is equal to our initial value of 30,000, 1 plus our rate of 0.032 to the power of t. Now to simplifying that, now we're going to have D is equal to 30,000, 1 plus 0.032 to the power of t. That's going to be Dan's annual salary after t number of years. Now looking at part C here, a population of 1 million bacteria in a petri dish is growing at a continuous hourly rate of 8.6%. Let B be the number of bacteria in time t hours. So we want to use our compounding continuously equation. If I spelled that right, I don't think I did. I think I did actually. So that's equal to our B for bacteria is equal to our initial rate, so I'm going to say B0, e to the power of our rate times our time. Where in this case, our rate is equal to 8.66%, but to plug it into our equation, we need to have it in the form of a decimal, so we're going to divide by 100, and have our rate is equal to 0.0866. So now plugging everything that we know into our equation, we're going to say our B value is equal to our initial value of 1 million, e to the power of 0.0866 times t, and that's going to be the number of bacteria at time hours compounded continuously. Now looking at part D here, we are initially, there was 100 milligrams of radioactive tritium, and it was decaying at a continuous early rate of 5.63%. Let R be the amount of tritium at t time years. So we're going to be compounding continuously again. So R is equal to our R0, e to the rate t. But in this case, we're decaying, right? So we're going to have a minus here to have our decay factor. It's going to be decreasing. So our rate, again, is at 5.63%. We want to divide that by 100 to get it in decimal form. So we're going to say 0.0563. So we plug in everything we know. The initial R value is 100, e to the negative 0.0563 t. So that's going to be the amount of tritium at time years compounded continuously. Now looking at our last part, E here, the cost of Ray's auto insurance was $400 in 2020 and has been increasing by $50 per year since that time. So this one doesn't have any exponential rate. We're going to use a linear function, which is like y is equal to mx plus b. So in this case, we want to write it in terms of I and t. So we're going to say I is equal to our rate of $50 per year. That's how much we're increasing every year. So times t. And then plus our initial rate, our initial value of 400. So that's going to be his insurance cost at each year. So I is equal to 50t plus 400. Okay, looking at question 10 here. An investment decreases in value by 5% per year for 4 years. Now what percentage does the investment decrease over the 4-year period? So we're going to use our rate equation. P of t is equal to P P0, 1, minus your arcs, we're decreasing, power of t, right? We want to know when t is equal to 4. So we know that t is equal to 4. We want to know P0 times this rate that it's increased is equal to P0, say R2 for that, 1 minus R to the power of 4, or this R inside here is at 5%, so we're going to say 0.05. P0 on both sides, that's going to be gone. So this R2, we're going to say is equal to 1 minus 0.05, which is 0.95 to the power of 4. So to find out what that R2, how much our P0 increased by, we're going to say 0.95 to the power of 4. It's going to give us 0.815. So to find out how much it decreased by, we're going to say 1 minus 0.81. What's that? 45. Do that and say 1 minus this. It's going to give us 0.1855, which is times 100. It's going to give us 18.55%, and that's how much that we have decreased by over the 4-year period. 55%. So now looking at question 11a here. So 11 says a sample of rock was found to contain a mixture of minerals, part of which were radioactive, decreasing over time due to radioactive decay. The mass of the rock in grams after t years is given by the function m of t is equal to 15 plus 3.8 times 0.785 to the power of t. So part A wants to know what was the initial mass of the rock. So what is the rock's mass at time is equal to 0. So what we're going to do is m of 0, and anywhere we see a t, we're going to plug in 0. I'm going to make this a little more clear. It's to the power. So we're going to have 15 plus 3.8 times 0.785 to the power of 0. So what's going to happen here is 0.785 is going to go to 1. So m of 0 is equal to 15 plus 3.8. So our mass at time 0 is equal to 18.8, and look back at the units, grams. Okay, next we're going to look at part B here. So what should the mass of the rock eventually become as time approaches infinity? So m of t is equal to 15 plus 3.8 times 0.785, the power of t. So as this t gets really large, since we have a decreasing, a decay function here, this 3.8 times 0.785 to the power of infinity, essentially, is decreasing. It's going to get really close to 0. So our m of t is going to be 15 grams as we approach infinity. Another thing graphically is we have is right here we have that 3.8. And as we're going this way, we have a horizontal asymptote here at 15 as we're getting really, really close to infinity.